So this is the last section we're going to go over. The review for the test is going to be on Thursday. Your test will be next Thursday. Remember, there's no class next Tuesday. I'm off for Veterans Day, so I'm not coming down for one class. So, but a lot of people have Veterans Day off anyway, so it kind of works out nice. On the 14th, so chapter 5's lesson in ALEKS will open after on the 14th and actually close on the 14th, and then after that, everything basically opens up. So you'll be able to go back and clean up any of the modules that you might not have finished previously, and do the Module 5 stuff. Module 5 stuff is part of your grade in terms of the ALEKS. There's just not a test on Module 5 or Chapter 5. It's integration. Everything's going to be due the day of the final. So at this point, basically, the day of the final, everything is due. So that's once I grade the final, I go back and I look at ALEKS and I put all the stuff in to the grade book at that point. So I do it that way. This way, everything opens up, so you have time to go back and fill in the holes and stuff that you might have missed in other modules while you're working on the Module 5 stuff. There are some issues with the specifically with the curve sketching. There's been quite a few problems that I've done where I've done the entire problem, I've submitted it, it's marked it wrong, I hit try again, and it's marked it right. So at this point, because of all the little issues with the curve sketching, I'm going to give you those topics anyway. So they will just be, I'll put those as in if you've done them as part of your grade, just because I know there's so many little issues with it that I don't know why they're marking them wrong. Yeah, when I did that one today or yesterday, and it literally had, I did nothing to it, hit try again, and it gave me to me right. I'm like, something's up. I did submit them to ALEKS to let them know that there's some issues with those. My guess is there's something with how they're actually looking at where the marks are on the graphs. I'm not quite sure though. Anything else? I will have the review test for you. I'll post it tomorrow. It's not going to be an ALEKS. It'll be on my website. This test is not going to be based on ALEKS. Yeah. Yes.
Sorry,
It's okay.
What did you say about next week?
There's no class next Tuesday.
Oh, okay.
It's Veterans Day, so.
Okay.
I don't. If you have other classes, there's possible classes. The college is technically not closed next Tuesday, so if you do have other classes, you have to listen to your professors for those. So yeah, I will post the review test for Chapter 4 on my website. Probably tomorrow. I'm going to go through and get all the rest of the videos and everything else up for this, and then I'll post the review test for you so you can actually start working on that. Next Thursday, the review test will start just like the last one. I'll be here at 4 o'clock. You guys can come early, start your tests. And when you're done, you're done. So, yeah. Yep. 3x5 note card or 4x6 note card. There won't be any curve sketching per se on it. It will be mostly like I'm going to ask you for pieces of it. So, like, I'll ask you for where it's concave up, concave down. I'll ask you for where increasing, decreasing, things like that. So there won't be any specific ones where you're going to have to draw me the entire graph. And it does actually become a little more heavy on the stuff that we're going to go over tonight, because this is actually the applications of all those curve sketchings. So there's actually 4 problems from this section actually on the test. There's only 10 questions on this test because these questions tend to take a little bit longer to do. All right, let's do the word problems. Optimization problems. You might have done similar ones to these in your pre-calc class when you were looking at the mins and maxes for polynomials. This is just extending that concept to be able to do any type of function. All right, so the first key in any kind of word problem is understanding the problem. Read the entire problem and find out what it's asking you for. Right? It's amazing how many times you won't read a problem, you just go through and you assume it's doing something and it's asking you for something totally different. So make sure you read through the entire problem, make sure you understand what it's asking you for, See what they gave you, what they're looking for. Draw a diagram. A lot of these drawing pictures definitely will help you do these problems, just like the last one we were looking in chapter 3. Drawing pictures can be very helpful. Your notation. You do not have to make everything X's and Y's. Especially when you're doing word problems, pick letters that make sense for them. Don't, like, pick things that make sense for the problem. So when you get your answer, you're like, okay, that's what this means. Sometimes X's and Y's works, but they don't always have to be. When you're doing the quantity you're looking for, that you're looking to minimum or maximum, it needs to be in a way that you can solve it. So like solving it for a specific variable, or getting the problems in a way that we can do implicit differentiation, those type of things on them. If it's been expressed in more than one variable, using those relationships to simplify things down, use substitution, elimination, those methods that we've done from in algebra and whatnot. The last thing is realizing that you have a domain restrictions a lot of times on a real life situation problem. So your minimum or maximum could be at the endpoint. It does not necessarily have to be in the middle on the curve. They could be one of the endpoints. So looking at the endpoints as a possible minimum or maximum as well can be useful. All right, most of it is just the standard how you solve word problems. All right, let's look at some. The wonderful fence problem. Start with the easy one. Farmer has 2,400 feet of fencing. He wants to fence off a rectangular field that borders a straight river. He doesn't need fencing along the river. What are the dimensions of the field that will have the largest area? How are you going to set it up? So what's the first thing you might want to do with this problem? Yeah, let's draw a picture. So we've got river. Fence. All right, and we're looking for, so now let's put some information on the graph so we can start figuring out what we're doing, right? We're looking for the area inside of it. That's what we're looking for. So the area of a rectangle is what? Area is length times width. All right, so what do we got? I know my perimeter. So we'll say that's width, and length, right? So that means 2,400 equals L plus 2W. So now we've got our two equations, right? We somehow got to relate them together. We're looking for area, so let's put everything into area. The way this one's set up, it makes it really easy to solve for L. So I can have 2,400 minus 2W equals L. So that means area is 2,400 minus 2W times W. So how am I going to find my in this case, we're looking for a maximum value. So how am I going to find my maximum value for this one? Okay. If I set area to 0, is that finding me my maximum value? Or is that finding where my area would be 0?
Oh,
There actually is a method to get to the answer we want that way, but that's more of the pre-calc method because you find the two x-intercepts and then you find the average of them because it's a parabola, which would work out well for this problem, but not necessarily the easiest way to go about doing this one. So now thinking of that calculus way, what method do we have for calculus to be able to find the mins and maxes?
finding the zeros of the derivative.
Right, we're going to find the zeros of the derivative. So I got to do the derivative first, then find the zeros. That's going to give me my horizontal tangents, which would be a minimum or a maximum point because that's where it changes direction. So we're going to look for our critical numbers once I find the derivative. So the derivative of A is 2400 minus 4W. Now set that equal to 0. Actually, let's do it this way. So I have negative 4W equals negative 2400. So W equals 600. I only have one critical number in this problem. So if my width is 600, we now need to figure out my length. So we can plug that back into here. So 1200 equals L. So then we can multiply those two. So my area equals 72,000 feet squared. Now in this problem, there is endpoints that also could work. However, the endpoints are going to be where all defense is used on either the width or the length. So my area would end up being 0 in those cases. So therefore, those would not be considered a maximum value. So we don't necessarily have to worry about that endpoint. So the maximum area would be 72,000 square feet. And the length would be 12,000 or 1,200 square feet. And the width would be, oh, sorry, I missed that. 720,000. I was off by a zero. And the width would be 600 feet. So now that's, if we look, what's the question asking for? They're asking for the areas, they're asking for the dimensions. Right. So this is where it's important to read what you're asking. We found the area just because we needed to find that to make sure that that's the maximum. But the question was actually asking for is 600 feet by 1,200 feet. And I know quite often in Alex, they will switch up what it's asking for. Sometimes it'll say, what's the length? Or what's the width? And if you answer the wrong one, you'll get it wrong. Yes. This right here. So power roll. So 2,400 becomes 2,400 or W. W goes away. Then we bring down. We're just using the power roll on it. Then we set it equal to 0 because we're looking for our critical numbers. And the critical numbers in this case, I just brought that over to that side. 24 and 26. Oh, that's 24. It's not 26. It's just the way I wrote it. And then 2400 divided by 4 is 600. Okay.
So because there's only one, the dimensions, like you said.
Yeah, the domain.
Zero, not the dimension.
Yeah.
Domain. Zero, that region. So
That's the maximum. Yeah. That's actually an absolute maximum in this case.
Yeah.
It's not even a local maximum. It's an absolute maximum. Yeah. The endpoints for this one would have been 2400 for the length, which would have left 0 for the width. So 2400 times 0 would be 0, or 1200 for the width, which would have left 0 for the length, and that would also be a 0 area. So it would have been 0, since we're solving this in terms of W, but the domain would be 0 to 1200. So. All right. A cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. So if we're looking to minimize the cost, in essence, we're looking for the least amount of material, right? Okay, so if we're looking for the material to make the can, what are we looking for in terms of the can? The surface area, not the volume. We have the volume. The volume is going to be 1 liter. We can use that. But we're really looking for the surface area. That's the thing we're going to minimize. So surface area, does anybody remember the surface area for a cylinder? Okay, so yep, it's a circle. So we've got, how many circles do we have in the can? 2. So it's 2 pi r squared, because that's the area of the bottom and the top. And now we need the around the outside, which is the diameter, or sorry, the height times the circumference. Yeah. So that's the surface area. And then the volume of the cylinder is pi r squared times height. Now, this is something that you might not know if you don't know metric. 1 liter is the same thing as saying 1,000 centimeters cubed. So 1,000 cubic centimeters is 1 liter. That's important because my dimensions are all going to be in centimeters and not in liters. So that's one of those things you might need to know. Now, if for some reason this question was on the test, I would have given you that. That would be an actual statement. You would not need to memorize that. All right, so we have 1,000 equals pi r squared h. And then we have the surface area equals 2 pi r times r plus h.
So she said you got a top, you get rid of it, as for the X bar, top bar.
On that one?
2 pi r squared plus.
Oh, the second part? No. So so this is the two ends. So pi r squared is at the bottom, pi r squared is at the top. That's why I have two of those. This one here is the height times the circumference, which is 2 pi r. The circumference is just 2 pi r for a circle, or pi d. Doesn't have to actually to factor it out in the next piece. All right, so what do you want to do next? Yeah, it's probably going to be easier to solve for h. Because then I don't have to do a square root. Which we then can plug in over here. So I'm just going to write this as a instead of SA. So we don't have two letters when we're bringing this through. So I've got 2 pi r squared plus 1,000 pi r squared times 2 pi r. So this is where cleaning things up is definitely going to help me. All right, so what's the next step? We've got the surface area formula.
And the derivative.
My derivative. So I've got 4 pi r plus so I can change that to minus. All right, next step. So that's the derivative. What do I do next? Yep, set it equal to 0. All right, how am I solving this for 0? Yeah, so there's a few different ways we can do it. Well, we can move it over first, or we can get rid of the fraction. I will get rid of fractions. Whenever I can get rid of fractions, I'm going to get rid of fractions. So if we multiply the whole problem by r squared, I get 4 pi r to the third minus 2000 equals 0. If we moved over the 2000 r squared first and then multiplied by the r squared, it would come up to be the exact same thing with cross multiplying. So it's not really, this is just nicer. So it's the third root of 500 over pi. How? Huh?
Yes.
Um, oh yeah, I could. In all honesty, in this problem, I don't think it would really matter. If they're going to want you to get an exact answer or an answer, they're either going to accept this or they're going to want it as a decimal answer anyway. And a lot of times when you're doing like a real life type situation or these type of problems, you're going to want them as a decimal anyway, because that's how they're going to be used to produce it. So all right, so I also need to find my what was the question asking? Find the dimensions. That will minimize the cost. So for the dimensions of the can, I need the radius and I need the height. So we have the radius. So now I just need the height. So I can plug the radius back in over here. This is a very convoluted way to write this, but it's kind of funny. So hold on. That's what I want, right? Okay. I can write this as 2 times 500 over pi. So it's 2 times the radius. That would be totally fine. I don't think you'd think to do that last step there. But this also is a really good reason on why, like, a lot of times you're just going to get a decimal answer as these answers. So if you've got that, not maybe we're going to come up with a decimal answer for this. But if you actually reduce that down to a decimal, it would be 2 times whatever the radius actually was. So the radius is gotten because of the 1,000, and then it's 2 times whatever that radius is. So, which is that big mess? Now in this one, the radius of the can, like, none of the information was given except for the volume. So I can't have, so the lowest I could possibly have would be 0 for my radius. So not including 0, getting infinitely close to 0. Technically all the way to infinity for my radius. So as you're getting closer and closer to 0 for the radius, your volume basically, or your volume gets closer to 0 because, or your height gets infinitely large to make the can still hold the liter, and the same thing on the other end of it. So since the domain is from 0 to infinity, we do not have any other restrictions on this one. Right. So, but if I can get infinitely close to 0 on the radius, but the height would have to be infinitely high to get the liter in there. So there's still a way to get it because it's not going to a single point. So unlike the last one where the area would actually go to 0, this one, it has an asymptote at 0 because it's going to get closer and closer to it to get that liter still in there. And the same thing on the other end of it. As the radius gets larger, the height has to get skinnier to make it still hold that liter in there. So. So, anybody ever paying attention to that space object that's coming by the sun?
Space object.
Yeah. What's his name? Hold on. 3i Atlas. Hold on, I'll show you. There really is an actual thing coming to the. I'm not totally lying. No, we don't know what it is actually. So this is the object. So it's literally, this is where it is now. So it's 3i Atlas is the object's name. So it's just coming around the sun. So actually it's made its closest path to Earth. I think it was yesterday or today. It was going to be making its closest path to Earth. So the reason I'm actually saying that is because the next problem actually relates to something like this that we're going to actually look at. So objects in space typically are in either elliptical orbits, or because they're so large, they end up looking almost like parabolic when they're coming in closer and closer to the sun. So like comets and things like that will come in close to the sun and then shoot out back. So it's an elliptical orbit, but at the end, we actually can look at it as almost like a parabolic arc at that point. So if we wanted to find the point on that arc that is closest to another point in space, say like Earth. So if we're looking at an asteroid coming through and we want to decide when is it going to get closest to Earth or is it going to hit us, this is in essence what they would do on a lot more complicated scale, because the equations are going to be more complicated than this, and they're going to be in 3 dimensions. But it's in essence the exact same concept. They're going to look at that equation for it, pick the point, and look for the distance equation to it, which is what we're going to do here. So if you go on through all your calculus levels, Calc 2 and Calc 3, Calc 3 actually looks at multivariable, which is basically taking all the stuff you're doing here and moving it into 3 dimensions. So you actually could do a problem like figuring out if an asteroid is going to hit the Earth and Calc 3. So we have a point on the parabola, and we want to find the point on the parabola that is closest to 1, 4. All right, so what do we need to do for this one? So here, let me actually, because I think a picture will help with this one. Like a can we could visualize. This one's a little harder to visualize. So here's the arc, and there's 1, 4. And we want to find the point that's closest to 1, 4 on that arc. So which formula or which equation are we going to be minimizing? The distance. Anybody remember what the distance formula is? That's the distance formula. All right. Nobody's going to say anything about that one. Everybody in here believes that's the distance formula. What is that? That's the Pythagorean theorem, which actually is the distance formula. You just expand it out to actually create it into space when you're looking at it. Because all a distance formula is looking for the hypotenuse of a triangle. So in essence, it is the Pythagorean theorem. We write it a little bit differently, though. That's the distance formula. But if you notice, it looks identical. It's the same setup as the Pythagorean theorem. So if you can't remember the distance formula, just remember the Pythagorean theorem, which pretty much everybody remembers. It's one of those ones that seems to get stuck in people's heads. At least I would hope, because all your trigs are based on it. But that's the distance formula. All right. Do we know anything? What do we know now about this? What do we know from this problem for the distance formula that I can plug in? Yeah, so if I have, we'll do x minus 1 squared, since I'm putting something in, I can get rid of this 2, and y minus 4 squared. All right. What's the relationship with the x and the y? Do I have something else that I can use to get rid of one of those? Huh?
Rooted that you do.
Yeah, we could take the square root of it. Okay. Yeah, I can just take. So the y would be the square root of 2x. So, but it's actually the plus or minus the square root of x, 2 squared root of x, right? Okay, that could be messy. So instead of doing that, do it the other way, which I think actually might make our lives a little bit easier, and then just do 1/2 y squared. All right. Find my derivative. Or do you guys want an easier way to do this? How would you go about finding the derivative of this? You could do that. I don't know. That was not an answer I was expecting. You'd have the ln of d. It might work out. I'd have to actually do it out. That might work out. I don't know if it's going to make it. It'll get rid of the absolute. It will get rid of the square root. What are we looking for? What are we looking for in this problem? We're looking for the minimum distance. If I wrote my Pythagorean theorem as this, if I minimized c squared, would that also be the same as minimizing c? Yeah, if we're looking at the square on that side of the Pythagorean theorem, right? If I minimize that, the length has to also be minimized at the same time, correct? Everybody agree with that? Because if you agree with that, then this problem becomes a lot simpler. Because that means I can get rid of my square root altogether. So as long as you understand that, we can just do this problem. We can find that derivative instead. And it's going to be the exact same thing. So we're going to minimize the square of it instead of the actual d. But since I'm looking for my critical numbers, the number is going to be the same for both of those. So I don't necessarily need to worry about that square root. Now I'm going to have to do the ln one tomorrow just to see if it actually does make this problem just as easy. All right, so it's my derivative of this. So we've got y. Oh, minus 8. I forgot to multiply that by 2. So now we set that equal to 0. So y equals 2. So I only have one critical number. Y equals 2. And if I plug that back into the y squared equals 2x, I get 4 equals 2x, so 2 equals x. So the closest point would be at 2, 2. And since the domain for this problem is all real numbers because the original function, we don't have to check the endpoints. And that's how scientists figure out when things are going to hit us. All right, read this problem. I'll show you the figure in a second. All right, try to draw a picture for it. How close was your picture? This is one of those ones that if you don't have a picture, it is going to be a lot more difficult for you to do this correctly. So the key pieces were the 3 there and the 6 there, or the 8 there. Those are the key pieces of information that you really need on your picture there. And then the question is, okay, well, which is going to be the fastest? Now, this problem, unlike the other problems that we've had, we do have some other values that could work. Okay. So let's look at those first. So it said she could literally boat directly across and then run to B, or she could row directly to B. So let's say she went from A to C first. That was 3 kilometers. And that's in a boat. So she's rowing 6 kilometers, right? So that would take her how long? Yeah, half an hour. And then if she ran from C to B, she did 8 kilometers and 8 kilometers per hour. That's 1 hour for a total of 1.5 hours. All right. So that's if she's rode directly across and then ran the rest of the way. How long would it take her if she rode the entire distance? What do we got to figure out first for that one? Yeah, so we have Pythagorean theorem, we can do this one, right? So I know a to b is the square root of 3 squared plus 8 squared, which is square root of 73. Divided by 6 equals so that's 1.42 hours. All right, so that's 1.42 hours. Next, we have to find out, well, what happens if she goes part of the way, right? So we need to find the optimal place to where she should land. All right, so now we have to come up with an equation. So what two lengths do we need to look at for this? Yeah, so we need AD, and that's rowing, plus DB, and that's running. So how do we figure out AD? What's that length? What did we do in the last one when we figured out AB? We used what? Yeah, so we're going to use the Pythagorean theorem again. Only difference is I don't know one of the sides. One of the sides is going to be x. So AD is going to be the square root of 9 plus x squared, right? And we're going to divide that by 6 for rowing. Now, what's the length of DB?
8 minus x.
Yeah, it's going to be whatever's left in here, right? And that's divided by 8. So that is going to equal time.
Probably there, do we take the derivative or do we have to do anything special?
Nope, we can do the derivative of this. The only thing I might do, just to make my life a little bit easier, I might change that to 1 minus 1/8 x. And that's only to make the derivative a little cleaner, so I don't have to do as much work with it. All right, find my derivative. That's what you should have gotten for the derivative. All right, solve for 0. Get it to you can get it to a decimal and round it 2 decimal places. So my critical number is 3.4 kilometers. Downstream. Am I done? Did I find what I was looking for? All right, let's go back to the question. We were trying to figure out the fastest way for her to get there, right? So we figured out that that's 3.4. But we still need to figure out the time because that's what we figured out the time for her going directly across and running or just going directly by there by rowing. So we need to figure out the time for this one. So we can go back to my original equation that I have here, the time one, and set x equal to 3.4. And we get approximately 1.33. So, what is the fastest way for her to get there? What is the way to minimize the amount of time she's using?
What's your answer?
3.4?
So she should land at point B, which is 3.4 kilometers off of point two.
And run the rest of the way. Because the other ones was 1.42. That's if she rode the entire way. And 1.5 if she rode across and ran. So it wasn't like drastically quicker, but it was a little quicker. All right, let's do one that's not geometry based. All right, so stores been selling 200 TV monitors a week at 350. Market survey shows that for every $10 rebate, the number of monitors sold is increased by 20. How large of a rebate should the store offer to maximize revenue? So we're not necessarily looking for profit in this case. We're just looking for a maximum or maximizing the revenue. So step one, well, we need two equations, right? The demand function which most of you probably have never heard as the demand function. It's also known as the price. And then revenue is X times the price function.
It's a rebate.
A coupon, taking it off, moneyed off. All right, so how am I writing my price equation? Because that's the most important one. This one. What kind of equation is price? What kind of function? It's going to be linear, right? Okay. So let's think about this as a linear equation. We have a point. 200 TVs is $350. Do we have a slope? Okay. Right, but if I'm so the price is $200, or the price is the function's not based on X is my price. Or X is the number of X is the number of TVs I've sold. So actually I think I have that backwards. I had that backwards. X is 350. No, I had that right. Yeah. X is the number of TVs that are sold. And they were $350 each. That's right. Because it's basically figuring out like, okay, if I'm figuring out that price, that where the point on the thing. So if I'm selling my TVs for $350, I'm going to sell 200 of them. So X is telling me how many TVs I'm selling, and the price, I'm coming up with my price equation based on that. That makes sense? Okay. All right. So if my price is Y and my number of TVs sold is X, think about your slope. Slope is rise over run, right? Y over X. So if my price is going, it's a $10 rebate, so that means it's going up or down. Down. It's like a coupon. So $10 off, and I'm increasing my TVs by 20. So there's my slope.
So what is the slope? And is that for the price function?
Yeah. I haven't done the revenue yet. Because the revenue is just putting an X in front of the price. Because the revenue is just how many I'm selling times whatever the price is. The price is what's actually going to change in this case. Wait, I did it. 250. Where's the 450? 450. Group in signs. All right, so that's my price equation. So that's P of X. So R of X is X times negative 1/2 X plus 450. Maximizing revenue. And X is the number of TVs sold. So if we look at the domain of this, that would make sense. I could have 0 TVs. Because I sold 0 TVs, that's at $450, but I'm selling 0 TVs. And the maximum amount of TVs that I could sell would be 900 TVs. Because if I put the price at 0, I sell 900 of them. Now, yes, realistically, that would not make sense. If I put the price at 0, I'm probably going to give away a lot more than 900 TVs if I had them. But anything more than 900, I'm going to go into the negative, and I can't have negative TVs. Or a negative price, I should say. But at both those situations, my revenue would be what? At both those situations, my revenue would be 0. Because either my price is 0 or the number of TVs I'm selling is 0. So neither one of those is going to figure into the actual problem at the end. All right. I would multiply this out so I don't have to deal with the product rule. How do I maximize things? What do I need to find? I'm looking for my derivative. Set that equal to 0. That was totally wrong. So X equals 450. Okay. So X was what? This is why sometimes using X's and Y's doesn't help me. X is the number of TVs sold, right? So I'm gonna, to maximize revenue, I need to sell 450 TVs. Is that what they're asking? No. They're asking for the maximum, how big of a rebate or how big of a coupon that I should offer. So what's the next thing we got to find now that I found the 450 TVs? Or 450 is the 450, the number of TVs is 450. I need to figure out my price. So we're going to plug that back into the price equation. So E of 450 is $225. So I should sell my TVs for $225. Is that what they're asking me? How much off? So now I got to take the 350 and minus the 225, which is $125. That's the answer. This is why reading the question is important. Because every one of those answers could have been the right answer for the problem, depending on how they were asked. This one's pretty simple because it's just a linear equation for the price. Not every demand equation is going to be a nice, simple linear equation. Yes. We did actually in the last problem when I did the boat. Yeah, we had to figure out the endpoints in that one. Yeah, yeah, which is in essence what the domain is, because she needed to get there. The two end ways that she could get there was doing the boat across or doing the and run, or just do the boat. Those are the two endpoints. The domain in this one didn't matter because each one of those would have resulted in the other piece being zero. So like if I had the price set at, if I did no, sold no TVs, my price would have been $450, but 0 times 450 is 0. If I sold, set the price to basically 0, I'd have sold 900 TVs, but 900 times 0 is 0. So either one of those would have come out to be a no on the revenue. So I didn't have that problem. All right, I will have the review test posted tomorrow. A sample of 10 questions, which we'll go over on Thursday. And then your test is next Thursday. See you Thursday.
Have a good night.
You too. Yes,
Really weird and duck question.
sure.